Okay, so today's topic, girls, is why molecules form particular shapes. So, in past lessons, we've been talking about electron dot diagrams and Lewis structures, but now we're going to move on to why they form particular shapes. Before we do some examples, we need to understand the reason why they form these shapes. And we take, for example, let's do water. We know that we actually get a bent structure for water. The reason why it does not form a linear structure is because of these lone pairs of electrons. And if we think about, let's use a different color for this, if we think about this, um, this, or the angle between each pair of electrons, so whether they are bonding or lone, I did it again, bonding or lone, it is 90 degrees. However, if it is in a if it is a bent shape, these valence pairs of electrons are actually greater than that 90 degrees. Bear in mind that this is a 3D structure for water, so it's a little bit hard to represent the greater angle, but when it does arrange itself in a 3D manner, the angle between the bonds and the lone pairs is actually greater. Why do they want to do this? Is because we know that electrons have a negative charge. So when we put two negative charges together, or positive charges together for that matter, they are going to repulse. So when a molecule arranges itself, it does so in such a way that the electron pairs in bonding pairs and lone pairs arrange themselves so that they're as far away as they can possibly be. What I've just said there is what we call the VSEPR theory, so the valence shell electron pair repulsion theory. Again, we are only looking at valence electrons, girls. We don't care about the electrons in the inner shells, we're only looking at the valence electron pairs. So we're not excluding lone pairs, that's really, really important. As I just said, doesn't matter if they're taking part in a covalent bond, or they're just sitting there doing nothing. They are negative charges, so they are going to repel. So what I'm going to do in this tutorial is I'm going to flick between this table and my sketchpad. What I really want you to look at is the bonding pairs and the lone pairs. So don't worry about the angles, the valence electrons and things like that. All I really want you to look at is the bonding pairs and lone pair of electrons. They're the two things that we are going to look at when we go through a couple of examples. So let's do an example. Again, I'm going to take examples from that sheet that I gave you the other day in class. So alright, COF2, this is the one that I finished with in my previous video on Lewis diagrams, but your first step for determining a molecular shape is to draw the Lewis structure for that molecule. So I'm going to save some time, draw it, but if you need any help, go to the previous video. But the Lewis diagram for COF2 is a double bond to oxygen, a single bond to one fluorine, and another single bond to another fluorine atom. So hopefully you should see it look like this. Now bear in mind that if you were just asked to draw the Lewis structure for a molecule, this is fine. I do not need to include valence electrons for the outside atoms if I draw it like this with dashed lines, but I do if, for instance, carbon had a pair of electrons there, I would have to include that, but we know it doesn't, so I'm just going to quickly rub those out. So this would be our correct diagram for the Lewis structure, and you'd get full marks for that. Now, what we need to look for in order to determine the molecular shape and then draw the molecular shape is the lone pairs of electrons, so the lone pairs of electrons, and the bonding pair locations. And this is around the central atom, which I've missed the word there, classic. But I need to look for the lone pairs of electrons, so I need to look for the lone and the bonding pair locations around the central atom, which in this case is carbon. When I look at this molecule here, I have 0 lone pairs. I have 0 lone pairs. I can see that because they're not represented there. All valence electrons are involved in a covalent bond. This is actually a really important tip, and especially when we get to hydrocarbons, girls, is that carbon should always have 4 dashes. Why? Because if it has to have a full outer shell, it should have 8 valence electrons. So remember, each pair is a pair. Each covalent bond is a pair of electrons. So 2, 4, 6, 8. There is no lone pairs in this molecule around the central atom. As I just counted, I have 1, 2, 3, 4 bonding pairs. However, I have 1, 2, 3. I have 3 bonding pair locations. Easy rule of thumb, when I'm counting the bonding pairs, I count a double or a triple bond. So even if that was a triple bond, I would count that as only 1 covalent bond, and that's how I get 3. So if we actually think about how this molecule can arrange itself so that the angles between the bonds are equal and also as far apart as they can possibly be, this oxygen has to move, because obviously it's quite far, it's 180 degrees from the fluorine covalent bond, but it's relatively close to this one here. So it actually can arrange itself in such a way that they are more spread apart. Unfortunately for this topic, you do have to remember the particular shapes. As you begin to use them more and more, it does become a lot easier. But at the start, I think if you can print out a table, girls, or maybe have your book open, you should always just have it there, so you can basically relate that to the molecular shapes that we wrote down in class. So the 4 shapes or 5 shapes? Let's have a look. The 5 shapes that we need to learn, girls, are the linear shape, the trigonal planar shape, the tetrahedral, the trigonal pyramid, and or I call it the pyramidal shape, so don't worry about that, that's the pyramidal shape, and the bent shape, or the V-shaped. What we simply need to do now is, if we go back to my sketch, if I go back to my screen sketch, I have 0 lone pairs and 3 bonding pairs. So going back to my table, I can see that a trigonal planar molecule has 3 bonding pairs and 0 lone pairs. So I need to match up my information with this table and determine that this would be a trigonal planar molecule. So I know this is going to be therefore it is a trigonal planar molecule. So we've named it, and if we want to draw it now, I'm going to draw it like that Mercedes symbol with basically it's just like a triangle, and we can determine that this is a trigonal planar molecule. Quickly do one more example. Okay, another one we had trouble with in class, girls, was dinitrogen monoxide, so N2O. Now, to draw my valence on my Lewis structure, I count my total valence electrons, which will be 5 each for nitrogen, so it'll be 2 plus 6 for oxygen, which is equal to 16 valence electrons. I can quickly go and draw my Lewis structure. Now, the reason why nitrogen goes in the middle and not oxygen is because nitrogen has the highest valency. Remember, the valency of nitrogen, use a different color, the valency of nitrogen is 3, whereas the valency for oxygen is 2. Therefore, the molecule or the atom with the highest valency goes in the middle. Going back to my Lewis structure, I quickly connect the two of them. That's using 4, and then I'm going to put valence electrons around the outside atoms. At the moment I have used 2, 4, 6, 8, 2, 4, 6, 8, so 16 electrons in total. Now, what I need to do is I need to move a pair of electrons so that each, or rather the central nitrogen, has 8 electrons. Again, in a similar fashion to what I did with COF2, nitrogen has the highest valency, so I'm going to actually move 2 electrons, or 2 pairs of electrons. I have 2 pairs of electrons moving from outside the nitrogen into the middle, forming a triple bond between each nitrogen atom. Now this is my correct atom or molecule structure, my correct Lewis diagram for N2O. Alright, so now I'm looking at, to determine the molecule shape, the number of lone pairs and bonding pair locations. So for N2O, I have 0 lone pairs. I can see no lone pairs around that one nitrogen atom. So I have 0 lone pairs, and I have 1, 2 bonding locations. We can start to see the shape already. But if I go back to my table, a molecule that has 2 bonding pairs and 0 lone pairs is a linear structure. So going back, my molecule will be a linear shape, and I can draw the shape by simply going a triple bond here with nitrogen and oxygen there. That is my correct answer for the linear molecule and drawing it there. Cool. Hope that helps.